Okay, so now that we've gone over what continuity is, discontinuity, and then the different types of discontinuity, let's actually do an example now. So it says to use the graph below to answer the following parts. So here I have this graph of f, and it says in part A to state the x values where the function is not continuous. All right, and then identify the types of discontinuity shown at each x value. Okay, so now looking at this, if you were to physically draw this graph, and I'm going to trace it so you can kind of visualize it here, but if I were to physically go, which I'm going to do now, draw this graph, right, I see that I don't have to pick up, sorry about this, I don't have to pick up my pen off the paper, right, until I get here at x equals 1, right, so I know that the function is not continuous at x equals 1. Okay. And then when I keep drawing this graph, right, where's the other part that I have to pick up my pen off the paper? And hopefully you guys see that that's at that value, x equals 3, where I have to then again pick up my pen off the paper to keep drawing this graph. So the two values here are at x equals 1 and x equals 3. Those are the two values where the function is not continuous. All right, and I just want to note to you that the function is continuous at all other x values except, at all x values except x equals 1 and x equals 3. Okay, so the reason being, right, is because I could draw the rest of the graph without picking my pen off the paper, except at those two values. Okay, so again, that's how we informally define these things. And so now, going back up to the first page, looking at these nice drawn examples here of removable discontinuity, infinite discontinuity, and jump discontinuity, which one do you think x equals 1 is and x equals 3 is? So pause the video at this point and try to figure that out on your note. Okay, so coming back, we see that x equals 1 is jump discontinuity, right? Because you can see that gap in between those two pieces of the function, right, at x equals 1. And then at x equals 3, we would say that this is infinite discontinuity. Or, like I said, College Board, we could say that this is discontinuity due to a vertical asymptote. Okay, so you want to make sure that you're familiar with both of those things. Okay, and then part B says determine the intervals where the function is continuous and use interval notation. Okay, so like I was saying, right, here when I gave you this note, the function is continuous at all other x values except these two values, right? So how would I write that using interval notation? Okay, well, I'm going to start with negative infinity and go all the way up to where my first x value is excluded. So from negative infinity to 1, I'm continuous. And then I'm also continuous from 1 to 3, right? So now I'm going to go all the way from 1, not including 1, to the next value where I'm not continuous, which is 3. And then not including 3, I'm continuous everywhere else, right? And so that's why I have from 3 to infinity. Now these little U-looking things is what we call in union with, and then it just brings all of the 3 different pieces that I had in interval notation together. So that's how we more formally write that. Now if you wanted to in set notation, although I specifically asked for interval notation, but we might as well go over set notation. How I would write this using set notation is I would use the bold R for all real numbers, All right, so in mathematics, to say all real numbers, we write this bold looking R. And then I want to exclude these two values, so I'm going to write all real numbers minus, and then in curly brackets, 1, 3. And so that's how I write it in set notation. Okay, so now let's talk about the formal definition of continuity. All right, so now we're going to get more formal here. Okay, so the formal definition says the function f is continuous at x equals some value c if all three parts hold. Okay, so here in part 1 I should say, it says f is defined at x equals c. So what does that mean? So I'm going to write here, what that means is that f of c is a number. Okay, and so that means that when I plug in c into the function and I get out a number, that means the function is defined at c. That's what that part means. Okay, if I plugged in c into the function and did not get a number, I got undefined, then we would say the function is not defined or undefined at x equals c. Okay, so when you're checking the first condition, you want to plug in that value, in this case c, into the function and make sure that you get out a number. All right, and if that's the case, then we're good. Function's defined at c. All right, and then the second part says that the limit as x approaches c of the function has to exist. Okay, and then for part 3, that the limit as x approaches c of f of x has to equal f of c. So whatever number you get out when you check the first condition, that number has to be equal to the limit. And if all three of these conditions hold, then we say the function is continuous. Okay, so you might be wondering why we have to be so formal with this. Mostly it's because mathematicians like to be very precise. Whenever someone goes, oh, but what about this case scenario? We have an answer for it. Okay, so sometimes, like, you know how you hear, like, oh, the rule doesn't apply to everything? Well, mathematicians like to make a rule that does actually apply to everything. So basically that's why they like to be more formal. But what's good about this formal definition for us, other than mathematicians being mathematicians, right? You're like, well, what's the importance to me? Really, it's super powerful because this definition tells us that if a function is continuous at c, then we can determine the limit by just plugging in c into the function. All right, so this is going to be huge for us in terms of computing limits algebraically, but we're not quite there yet, so we'll come back to it. But this is very useful for us. Okay, and so now we have types of discontinuity, formal definition. Okay, so now we're going to be formal too about the discontinuities that we've defined here. So what does this say? It says if f is discontinuous at x equals a, that one of the following holds. Okay, so either f has removable discontinuity, f has jump discontinuity, or f has infinite discontinuity, right? So we talked about that already. Those are the three different types. Now, the formal part that we see, in part 1, it says that if the limit as x approaches a of f of x exists, but the limit is not equal to f of a, that's what we call removable discontinuity. Okay, so this will be easier to understand a little bit more when you kind of explore this a little bit more graphically, that you can get a better visual for this, because right now this is a lot of notation. But as far as the second one, as far as jump discontinuity, it says f has jump discontinuity at x equals a if the limit from the left and the limit from the right both exist, okay, but they're not equal. Okay, so in other words, the left-handed limit is a number and the right-handed limit is a number, but the numbers just aren't equal, right? So not only will we say the limit doesn't exist, but now we can say that there's jump discontinuity there at x equals a. Okay, and then the last one here is f has infinite discontinuity at x equals a if the left-handed limit or the right-handed limit is some form of infinity. Okay, So this is a lot, but I will, in the next video, go over practice so we can get more practice.